So last time we have introduced the Reynolds transport theorem, and we said that this theorem can be applied to different variables to come up with conservation equations. So what we will do in this session is that we will start to practice on the Reynolds transport theorem. The first application is the continuity or conservation of mass. Then we will apply like the Newton law. So when we take for B equal to V, we will obtain the equation of momentum conservation, as we'll see together. And another important application also is the energy conservation, which can be derived also from Reynolds transport theorem. And a particular case is the Bernoulli equation that you are already familiar with. Okay. So this chapter is just a practice of the Reynolds transport theorem for different applications. To remind you, we developed the following Reynolds theorem last time. Just here it's big B, okay? And here, if you want, this is similar to small b that we took together. Here they represented as best, okay? So we have seen that the variation of a property for a system is equal to the variation of the property within the control volume plus the sum of fluxes crossing the control surface of the control volume. Okay, so to start with, we will consider examples for conservation of mass. And I will try to illustrate more the difference between control volume and control mass if it's not clear for you. So for example here, let's say you have the following flow system and you are interested in this zone of space. This is your control volume. And what the dotted line in red is the control surface. Okay. Now, you should always know that when we talk about a system, the system is defined as a certain fixed mass that I follow with time. So this is why the concept of the system might be more complex for you than the concept of control volume. So you can consider, for example, that at a certain instant, what was in the control volume was my system. Okay. Now, if you follow it with time, these particles will take new locations because some particles will get inside of the control volume, so they will push these particles, okay, while others will get out. So when if you want to follow a certain mass of particle, it will take a new position after a certain period of time. So let's say it will take, for example, this position, because these particles will be, the particles from this side and this one will be pushed by new particles coming in. And some of the particles that were inside of the system that were inside will get out. Okay, so the control system here, if we want to follow it with time, its boundary is varying with time. While for this case, the control volume is fixed. So at any time t, this is your control volume. So this is an example of fixed control volume and moving control system. Okay, now, whenever I talk about a system, since I define the system as a fixed at a fixed mass of same particles that I am following, this means that when I do del m by del t, this term will cancel out because, as we said, this mass is fixed. So always when you apply the conservation of mass, the first term of Reynolds transport theorem will cancel out because the derivative of mass for a system is 0. Now, for a control volume, it can be 0, it can be different than 0. It depends on the application, if the application is steady or unsteady. This application is steady. Why? Because you have constant m dot in and constant m dot out. So always the mass flow rate coming in is not changing, and therefore also for the mass flow rate getting out. Okay. So what will happen, like, for example, if you have 2 kilograms per second coming in from this side and 3 kilograms per second coming in from this side, then at the outlet you will have 5 kilogram per second. Okay, so if you apply the Reynolds transport theorem, since it's a steady application, the second term will cancel out also. So you will only deal with the fluxes crossing your surface. And as we said, when you account for the fluxes crossing your surface, you should consider the relative velocity of the fluid, of the particles with respect to the control volume. Here, since the control volume is fixed, then the relative velocity is equal to the absolute velocity. So because the control volume has a velocity of 0, so if the velocity, for example, at section 1 is 2 meters per second, then the fluid will enter the control volume at 2 meters per second. However, if the control volume, for example, was moving at 1 meter per second and the flow moving at 2 meter per second, what will enter the system will enter it at 1 meter per second, because I should consider the difference between the velocity of the flow and the velocity of the control volume. Whenever the control volume is fixed, V relative and V absolute is exactly the same. Okay, so in this example, we end up with the following. We end up with minus sum of m dot n, because all fluxes getting in are considered negative, because v dot n at n inlet is negative, as we have seen in last time, plus sum of m dot out equals to 0. Okay, so this will give us what is expected, that due to conservation of mass, sum of m dot n is equal to sum of m dot out. Okay, any question on this? Now, another example of mass, of continuity or conservation of mass, is a balloon in inflation. Okay, so if you have a balloon in inflation, this means what will happen in this case? You have a flow continuously getting in it. So what will happen here is that the control volume will vary in geometry, because you will have expansion of the volume. So this is an example of control volume that is variable in size. Okay, so with time, the volume occupied by this control volume will increase, and the control surface is the boundary of the balloon. This is your control surface. Okay, now if you want to apply for the balloon the Reynolds transport theorem, again, okay, here what is the system? The system consists of let's say, if you have, let's say, a reservoir, for example, you have a reservoir of gas. So you can consider that your if you want, your system was what was in the reservoir plus what was in the balloon at the initial state. Okay, so this quantity will not change with time, because what will happen is that what was in the reservoir will the mass in the reservoir will be reduced to go to the balloon, but in total, okay, what will leave the reservoir will get in the balloon. So these particles will conserve their mass, but they will change in location. Okay, so when we do del by del t of the mass that we are observing, okay, it's also 0. Now, our control volume is the balloon. Now, for the balloon, the quantity of particle inside the balloon is changing with time. Because this quantity is changing with time, this term now will not be equal to 0. Okay, so del by del t of integral control volume rho dv is different than 0. Okay, and it is here it will be a positive value, because I am continuously introducing gas to the balloon, so the mass of gas inside the balloon is increasing, and I don't have any outlet to discharge this gas. So only I have accumulation of mass. Okay? So this term here in this example will represent the accumulation of mass in the balloon. Now, if you assume that the density of gas at any instant is constant, like the example, if you remember, we did last time, if the rho is uniform, is the same with respect to space, I can take it outside of the integral, and then I will obtain that del by del T of rho integral over the control volume of dV. Integral over the control volume of dV is the volume of the balloon. So this is volume of balloon. Okay, equal plus what? Plus, now this term is due to fluxes crossing the control circle. In this example, as we said, we only have a flux getting in, okay, inside the balloon. So because it's an inlet, V dot N is negative, so minus M dot N equals 0. And now we obtain a physical result, which is expected, that the variation of mass in the balloon, so rho times V balloon, represents the mass of gas in the balloon. So del M balloon over del T, the variation of mass in the balloon is equal to M dot N, which is expected, because the rate of variation of mass inside the balloon is equal to the rate of mass entering the balloon. Okay, so these are some examples of steady and unsteady cases for continuity equation. Now, if we want to write this in equation for the, if you want, for a similar problem, so we have here the balloon and we have one inlet for it, as we said. Okay, always dm by dt for the system is 0. This is the accumulation of mass in the balloon, and this is the fluxes of mass. Okay, so here if we write the equation, we can write that dm by dt of the system is equal to d by dt. Now, what is the volume of a balloon? It's a sphere. The volume of a sphere is 4 over 3 pi r cubed. And for m dot n, you know that the mass flow rate is rho times A times V. Okay, if we consider a uniform inlet. When we say for you uniform inlet, this means that the velocity is constant at the inlet. Okay, so you can say that m dot n is rho at section 1 times area of section 1, which is the inlet, times velocity at section 1. Now, if we want to continue this relation, this is a complex relation, okay? Because look, you have that rho might vary with time. The density inside the balloon might vary with time, and the radius of the balloon is varying with time. So to be able to solve this equation, we need to know some other properties. We can do some experiments maybe to be able to solve such problem. Okay, so we say that we need to know the pressure, temperature, and elastic properties of the balloon, which can give us more insight of how to solve this, because this will help us to know how the density is varying and how the radius is varying with time. Okay, so we cannot solve this problem if we don't have additional mechanics and thermodynamics relations. So what I am interested now is to know how to reach this state. Okay, once I reach this state, it's fine for me. So what I want from you is to know to express this relation. Now, to be able to solve for rho or for r, I should know additional properties. I should use other sciences to be able to find the rho function of time and the r function of time separately. This equation will allow me just to find the product rho b, because if I integrate with respect to time, I can say that rho balloon function of time times RT to the power 3, if I integrate, is equal to This is a constant, okay? So is equal to 3 over 4 pi times rho 1a1 v1 times t, okay? Plus constant. And to know the constant, I need to know initial boundary condition. Now, if I want to know separately rho function of time and R function of time, I need further information, further equation to close my system. Okay? Any question until here? Okay. Now, to remind you, we said that if the control volume is moving, then to know what is the mass flow rate crossing the control surface, so getting in or getting out, I must find the relative velocity, which is the velocity of the fluid minus the velocity of the control surface. Okay? So remember the example of the pipe and the jet. So if you have a pipe moving at 10 meters per second and the jet moving at 10 also, nothing will enter the system because water will not be able, they move at same velocity, so it will not be able to reach it. Why? So we need to have at least a velocity here larger than 10 so that the flow can enter. So for example, if
Doctor?
I take 15 here, then the flux crossing the surface will be crossing it at a velocity of 5 meters per second. Okay, this is why
Doctor?
yes.
Sorry, should we send on the group for the students to join? Because it's not class time.
I said to join on the group. I said we said from 2-3 hours that the class is at 5, and I repeated at 5 that the class will start. You didn't receive the message.
We didn't receive anything.
Oh, sorry. Because it's sent from my side. ما بعرف لما وصل لكم بركي في مشكل بالواتساب, but it's sent from my side. I said, dear students, let us start the session.
Okay, it's okay.
Sorry if it was not. بس نحن قلنا.
No, it's fine.
Okay, it's fine. Anyway, it's recorded, okay?
We have a presentation today. We want to do it.
Ah, sorry. Look, you are not from the fluid class, ما هيك؟
لا نحن ال ENST 300.
Okay. Look, leave now and I will tell you when to join, okay?
Okay, sorry.
No, it's fine. Bye. Okay, so let us continue. Okay. So, as we said, if we have a moving control volume, then we should consider relative velocity, which is the velocity of the fluid minus the velocity of the control surface. Okay? So now, if I consider for a moving control volume the equation, all I have to do is to replace the v dot n to consider the relative velocity component and not the absolute one. So if you want, always use this expression. This is general. لأنه in case the control volume is fixed, what will happen? V control surface بتكون 0. ساعتها V relative بتكون equal ل V absolute of the fluid. And in case it's not constant, it will also work. So this will always work. So this is why we'll use in general integral rho V relative dot n dA in all cases if the control volume is fixed or moving. Because when it's fixed, just the velocity of the control volume will be 0. And when it is moving, I will replace the velocity, the absolute velocity I should subtract from the absolute velocity, the velocity of the control volume, to get what is the velocity at which the fluid is crossing the control surface. Okay, and we have demonstrated in last session why v dot n will always work for inlets and outlets. So if you remember, we said that always for outlet V dot N is positive, while for inlets V dot N is negative, and this is what I want because fluxes coming in are counted as negative and fluxes getting out are counted as positive. Okay. And in case I have a certain inclination with the surface, so if this is angle theta, okay, then all I have to do is to say that I need to project V on N. So this will be, in general, theta is given between V and N. هلا إذا أكيد إذا أعطوكم this angle you do 90 minus. So if this is theta and this is your velocity, then you should project V along N. So you should do V R cosine theta. Okay. Okay. Now, let us take another example. Okay. If I consider the following control volume, I have a control volume in a triangle form. And I have a constant density velocity field characterized by U component of velocity, which is the component of velocity along x, equals to V0 x over L. V component of velocity is 0, and W component of velocity is minus V0 z over L. Okay. Now, I want to use, and the control volume has a certain depth B with the phase. Okay. I want to compute the volume flow through sections 1, 2, and 3, and compare to see whether mass is conserved or not. So my purpose is to check if I have conservation of mass in this problem. Of course, conservation of mass should always be applicable. If it's not applicable, this means that there is something wrong. Okay. So in case here, as I can see, the flow is steady because it's not function of time. So because the flow is steady, I expect that sum of m dot n should be exactly equal to sum of the m dot out because nothing is accumulating in the control volume. Let us verify this. Okay. First, let us start by section 1. Okay. At section 1, this section is of length L, okay, and is of width B. So the area is equal to L times B, okay? Now, in order to compute the mass flow rate, compute m dot 1, okay, what is the procedure? M dot in general is integral. Okay, let us apply the formula. It's integral rho V relative dot N dA. Okay, now let us see what is V relative in this case and what is the elementary mass dA. First, velocity along section 1. Okay, if you look at the expression of your flow field, for your flow field there is no component along y, so always y component is 0. You only have u component and w component. Okay, now this section 1 is characterized by what? It's characterized by z constant. Okay, because this plane is parallel to xy. Okay, so this plane can be written as the equation of this plane is z equal to L. Okay, so while for this plane x is varying from 0 to L. Okay, so this surface of interest is characterized by z equal to L, and x varying from 0 to L. Okay. Now, if I go back to the expression of my velocity field, the component of velocity along z is w equal to minus v0 z over L. And because for this plane, z is constant equal to L, then w is constant equal to minus v0. Now, if I replace z by its value, which is L, so it's minus v0 L over L. L will simplify, and I deduce that in section 1, w is equal to minus v0. So I can deduce until now that for this plane, w is constant, v is 0, only u is variable. Okay, only u is variable, and u is varying with x. Okay, whenever you have a velocity that is variable, you should perform integration. Okay, but what is nice here, if you think a little bit, when you consider this section, you only care for the component that is perpendicular to the plane. Okay, because u component, it's true that u component is varying along the section, but u component is parallel to this section, and any component parallel to the section will not contribute to m dot. Okay, because it will not cross the control volume. So even if u is variable, it will not affect my mass flow rate, because it will not enter or exit the control volume. And if I apply the formula Vr dot n, okay, I will say that for this surface, what is n? We said that n is always perpendicular to the plane of the face and getting out of the control volume. So as you can see here, for this face, for face 1, n is along k. Okay, so I can say that n for phase 1 is equal to k. Now, for v relative, the control volume is fixed, so v relative equal to v absolute. And the velocity of the flow at this section was decomposed into u component and w component. And we have demonstrated that u component is variable, but it is along I. And w component is just equal to minus v0 as we demonstrated. So minus v0 k dot k. Okay. Now, what will happen now? Look, I dot k is 0. So whatever is u, I don't care. Okay? Because I dot k is 0 will cancel out. So I will just obtain that v relative dot n is equal to minus v0 k dot k is 1, so it's minus v0. So now I can perform my integration. No need to do any integral because everything is constant. I can take them outside of the integration. So I have integral rho, okay, times Vr dot n will be replaced by minus v0. So integral over area 1 of dA. And since rho and v0 are constants, I can take them outside of the integration. I can take rho and v0 outside of the integral. So I will get that m dot n is equal to rho minus rho times v0 times a. So as you can see here, you can know that it's an inlet because you got a negative result. Okay, So every mass flow rate that is negative is coming in, and every mass flow rate that's getting out is plus. Okay. So here, if you want, نحن بناخد m dot n as absolute, so you can consider that this is minus m dot n. Okay. So for phase one, the flux, I have a mass flux entering my control volume. Let us see what is happening at plane 3 and 2. For plane 3, also I have the width equal to b. I have the length here is L. So the area of my section is B times L. Now, this section has a normal vector perpendicular to the face getting out of the control volume. So as you can see, for this face, the normal vector is minus I. Okay, the normal vector is minus I. So now, what we will do, again, we'll repeat the same procedure, but for phase 3. Okay, phase 3 is characterized by what? It's a plane parallel to zy, okay, and it is at x equal to 0. So I can say that this plane has equation of x equal 0. If x equals 0, what will happen? U is 0. So at phase 3, U is 0. V is 0. I only have W. Okay? And since I only have W, look what will happen. I only have a velocity parallel to the face. If the velocity is parallel to the face, can it cross the control volume? Can I have an inlet mass flow rate or an outlet mass flow rate? When you have a flow parallel to a surface, can it enter the control volume or exit it? No, it cannot. Okay, and you can see this from the equation because m dot is integral rho v dot n dA. Okay, so here both velocity and the n are perpendicular, so no projection of velocity along un. This is why no flux will cross the control volume, because velocity is along k, wk, and the normal vector is along minus I. And you know that the dot product of two perpendicular vectors is 0. So this term will automatically be equal to 0. And this means that no flux will cross section 3. So until now, we just have one inlet here, and we have obtained the expression of m dot n. M dot n was equal to, getting inside, was equal to rho times V0 times the area of section 1 اللي هي L times B. Let us verify now, let us verify that at 2 we should have an outlet. فيكون في conservation of mass. Since it's a steady application, everything coming in should also get out. So we should verify that m dot out at section 2 is characterized by the same expression. Okay? So to do this, let us perform calculation. For section 2, it's an inclined plane. And this inclined plane has an equation. Okay? You have that for this plane, okay, you have a width b, and you have a relation between x and z. So as you can see, this line is a line of slope 45 degrees. Okay, so and it's passing by point 0, 0 and LL. So it's clear that the slope of this line is 1. So the equation of this line is z equal to x. Okay, So since z is equal to x, I can say that if I move along this plane, okay, I have that u is v0 x over L, and w is minus v0 z over L, or because z is equal to x, w is minus v0 x over L. Okay, and now I want to find the total mass flow rate. So what I will do is I should perform an integral procedure. How to perform this integral procedure? Okay, I will write integral rho times VR dot n dA. Okay, now first, what is n vector? N vector here is the perpendicular to this section. Okay, is the unit vector perpendicular to this plane. And as you can see, this unit vector has two components, one along z, one along I. The component along I is positive, the component along z is negative. So this unit vector n, so n for section 2, can be written as the normal vector n is cosine 45 along I minus sine 45 along j. Okay, and now concerning the velocity field, we have seen that it can be written as v0 x over L along I minus v0 times x over L along k dot product of n, so dot cosine 45i plus minus sine 45j. And now you can do the expansion. Okay, you can do the expansion by doing I dot I is 0, I dot I is 1, I dot j is 0, k dot I is 0, and k dot j is 0. So we have only, when you do the dot product, you will end up only with v0 x over L times cosine 45.
مش لازم تكون بالأخير كي الماينس ساين 45
نعم.
الماينس ساين 45 in the end factor.
لا minus ايه مظبوط معك حق. It's this is z صح. This is
Yes.
k. Exactly. So this is k. So when we do here k vectorial k, it's plus 1. وعندنا minus يعني plus v0x over L times sine 45. Okay. Look.